Hello students, let us start our today's session. From organic chemistry, the next chapter, aldehydes, ketones and carboxylic acids. These are all together known as carbonyl compounds. What do you mean by carbonyl? Carbonyl is a carbon with doubly bonded oxygen. So carbonyl group is generally represented as a C double bond O. In the previous chapter, we discussed about alcohols where the functional group OH is bonded to carbon through a single bond. Here we are going to learn about the carbon to which the functional group having oxygen atom doubly bonded with the carbon. So to this carbonyl group depends on the other two valencies of carbon satisfied, may called as aldehyde, ketone or carboxylic acid. Suppose in this carbonyl group, one of the valence is satisfied by hydrogen and other valency by an alkyl group, then it is termed as aldehyde. So the functional group of aldehyde is CHO. So this makes the functional group of aldehyde. And when both of the valencies of the carbon is satisfied by either similar alkyl groups or different alkyl groups, that makes the other class of carbonyl compounds ketone. In the same carbonyl, when one of the valency is satisfied by alkyl group and other valency by hydroxyl group, then it is said to be carboxylic acid and whose functional group is COOH. You may get this name carbonyl, you can get carbo, hydroxy we can get OXY. So when both hydroxyl and carbonyl present together, so it is known as carboxylic acid. Why the name acid is given? You know, the hydrogen present along with the oxygen that may have a tendency to lose from the carboxylic group. As it behaves like a proton donor, it is said to be an acid. So this is carboxylic acid. So depends on the two valencies of the carbonyl group of carbon atom, we may have aldehyde, ketone, carboxylic acid. And what the rest are? It is nothing. They are the derivatives of carboxylic acid. So carboxylic acid in which either the OH group or the hydrogen atom of OH group can be replaced by a suitable group from which we can get the derivatives of carboxylic acid. See, in this carboxylic acid, when hydrogen is replaced by the R group, that is an alkyl group, that makes the functional group of ester. At the same time, when hydrogen atom of the OH group is satisfied by an acyl group, then that makes the functional derivative of anhydride. This is said to be an anhydride structure. So anhydride means no water. So these two derivatives we got it as the replacement of hydrogen by either alkyl group or the acyl group. Suppose when the OH group is replaced by a halide, it is said to be acid halide, or the OH is replaced by an amine group, then it is said to be acid amide. So this chapter that includes aldehyde, ketone, carboxylic acid and their derivatives. Okay, why do we learn about this chapter? We know these compounds are widely spread in both animal kingdom as well as in plant kingdom. And what we eat, the spicy food and the fragrances what we smell from the food, these and all just because of the presence of this family only. So they have a fragrance in some of the compound, and some of the compound they may have some pharmaceutical value, and some of the compound that can even be used as solvents. So for example, the food that can have the fragrance because of vanillin, it is nothing but the vanilla essence. It is present in vanilla beans. See, you may find the functional group is aldehyde. As well as the cinnamaldehyde, the cinnamon, one of the spice that contains cinnamaldehyde, that's why we are getting that fragrance. And the salicylaldehyde, that is also present in meadow sweet. So besides that, they can also be used for some other industrial preparations of plastics, adhesives, etc. So this is the reason we should know about these compounds and why do the food become more fragrance, or why do the spices have fragrance and all. Okay, let us start nomenclature of this chapter. Before go to nomenclature, we should know how the names arrived for their compound, how their common names arrived for their compounds. See, most of the common names have been arrived from their sources only, and the sources also known in terms of their Latin name or a Greek name. From their carboxylic acids only we are getting their aldehydes and the corresponding ketone names. So first thing we should know what are the carboxylic acids derived their names, common names from their sources. See, we have formic acid in which it has only one carbon. So the one carbon containing first member of carboxylic acid is formic acid. Actually, this formic acid is present in the venom of red ant. The red ant, in Latin, it is called Formica. So from the Latin name Formica, we are getting the name formic acid, because upon the bite of red ant that we may find swelling and irritation and all. It is nothing but it injects that formic acid inside the body where it reacts with us to make swelling and irritation. And the next one, the next acid that contains 2 carbon atom of carboxylic acid is acetic acid. That term acetic is derived from acetum. Acetum is also a Latin word. Acetum is nothing but vinegar. The next one, propionic acid, in which that carboxylic acid contains 3 carbon atom, where propion belongs to the Greek term that means the first fat. And butyric acid that has 4 carbon atom in its structure, butyrum, that is called butter. The butter which is derived from butyrum, a Latin word. How the butyric acid is present? See, in butter actually butyric acid is present as butyrates, the ester. When butter goes rancid, that means gets spoiled, the butyrate hydrolyzed to form butyric acid and it produces that foul smelling. So from that we can identify the butyric acid which is present in butter. And the next one, valeric acid, where it contains 5 carbon atom, and this valeric acid from the Latin word valer, that means to be strong. And the 6th one, it has a 6 carbon atom, it is called caproic acid, in which the capr, it means goat, Latin word. See, some of the acids, they are present in mammals, that means the milk produced by mammals that contain some of these acids in the form of their esters, and hence see the caproic acid is present in goat milk, so the name is given caproic acid. So such a way most of our carboxylic acids derived their names from the sources, and the name arrived from their Latin or Greek only. Let us discuss about the nomenclature of aldehydes and ketones. So first member of aldehyde is HCHO. The first member of aldehydic family is HCHO. The second member you may find this hydrogen atom of the first member is replaced by a methyl group. So we have the compound having 2 carbon atom. Successively the hydrogen that can be replaced by methyl, ethyl, propyl, isopropyl, butyl or the isomer of butyl, whatever that may have in their aldehydic structure. So depends on the number of carbon atom present along with the aldehydic structure, we can give their common name, and just now we discussed these common names are arrived from their source of the name. How the name? It is actually HCHO formaldehyde. Just now we have seen the formaldehyde, that is its corresponding acid is formic acid. So from the formic acid only we got. So the formic acid, as it has 1 carbon and its corresponding aldehyde also has 1 carbon, so the name is formaldehyde. Acetic acid, we said 2 carbon containing. From the acetic acid, you may find the 2 carbon containing aldehyde is acetaldehyde. So acetic acid, acetaldehyde. Similarly, propionic acid, propienaldehyde. Butyric acid, butyraldehyde. So first few members of the aldehydic names arrived from their corresponding acid. Why do we call it as corresponding acid? Because the oxidation of these aldehydes, they form their carboxylic acid. Formaldehyde on oxidation, formic acid. Acetaldehyde on oxidation, acetic acid. Propienaldehyde on oxidation, propionic acid. So these carboxylic acid can be obtained by the oxidation of aldehydes. That too we may infer the name given from their aldehydic names given from their sources of carboxylic acid. And here you may find it has a phenyl group with the aldehyde. See, from the formaldehyde, the hydrogen atom is replaced by a benzene ring. So it is called actually benzaldehyde, but IUPAC name you can say phenyl methanol. So the common name of this compound is benzaldehyde. And the other one, there are 4 carbon atom and CHO and 1 more halogen is also present, in which when we say the common name, we have to identify their notations. Not supposed to make use of numerals. Instead of numerals, we have to use alpha, beta, gamma notations. So from where the alpha, beta, gamma, it starts in a compound. This is aldehyde, a functional group. The functional group attached carbon is said to be alpha carbon. So this is for me alpha carbon, and the respective carbon, the next 2 carbon atoms and all, I can designate as beta carbon, gamma carbon, like that. So in common names, to identify the position of the substituents or some other groups present in it, they can be called in terms of alpha, beta, gamma notation. And alpha carbon is the carbon very next to the functional group, or the functional group attached carbon is alpha carbon, and the corresponding carbon atoms are designated as beta, gamma, delta, like that. So in this case, the beta carbon, it has bromine atom. So the name it will be beta bromo. How many carbon are there? 4 carbon atom. So its corresponding carboxylic acid is butyric acid. So the name it is butyraldehyde. Similarly, these are aldehyde. You can go with the ketones. So in ketone, see the aldehyde, formaldehyde, it has aldehydic CHO. I have 1 more hydrogen in the aldehyde. That hydrogen can be replaced by another alkyl group. So the first member of ketone should have at least 3 carbon atom. We have aldehyde having 1 carbon atom, but in ketone family, the first member itself should have 3 carbon atom. Because the carbonyl CO group, you know, it never comes to the terminal position of the structure. But aldehyde, it can go with the terminal. Terminal means at any one end of the structure. So always the CO group should be in between of the substituent alkyl groups. So it never makes the terminal part. As it requires that middle of the molecule, definitely both the hydrogen atom to be replaced by alkyl group. So the first member is acetone. So the first member of 3 carbon having ketone is acetone. And how the common name, you can say even this is as one methyl, other methyl. So you can say it as dimethyl ketone. This is also its common name. And when you go here, you have one ethyl part and one methyl part. Once again, 2 different alkyl group, you have to name them from alphabetic order. So you have to say ethyl methyl ketone. So the name of the compound for this is ethyl methyl ketone. And here a benzene ring, in which one of the aldehyde you can find one of the hydrogen substituted by the methyl group. So you can say it is methyl phenyl ketone. Actually it is known as acetophenone. Acetophenone itself its IUPAC name. And in this case, instead of the methyl group, I introduced one more phenyl group. So it is called diphenyl ketone or it is benzophenone. Benzophenone is also its IUPAC name, as well as we can take it as common name for this compound. So under nomenclature, we have given common names for their compound, and when number of carbon increases, then the successive carbon atom very next to functional group is designated by alpha, beta, gamma, delta. For example, in ketones also you can designate them. This is the functional carbon, it is attached to alpha carbon. And the very next group is also the similar identical group. So how you will name it as, this is alpha, so it will be alpha dash. When we designate the alpha beta position for ketones, in acetone you may find both of the carbon are similar, methyl group, identical. So they are said to be alpha, alpha dash. But when you go to ethyl methyl ketone, the one of the carbonyl, the side it has a methyl group and other side it has ethyl group. So the nature of alkyl group differ. So this methyl it has alpha position, and in ethyl both of the carbon are designated as alpha beta. If you have propyl, it will be alpha beta. Then when will you find alpha, alpha dash? See, the compounds like C double bond O, CH3, CH, CH3, CH3. See, in this case, this is carbonyl group and it is an alpha carbon, and this is alpha carbon. This alpha carbon, it has 2 identical substituent. So this is beta, this will also be beta. So beta, beta dash we are giving. So to the same alkyl group, to the same carbon, when more than one alkyl group, similar groups are present, there only you can give beta, beta dash like that. If they are different, we have to go with different notations. So in methyl phenyl ketone, you may find it has one methyl group and a phenyl group. In benzene ring, all the 6 carbon atoms are identical, CH group only we have. So among these 6 CH groups, we can't able to differentiate as it is alpha or it is beta like that. So in say benzene ring, you can't able to designate them with alpha, beta, gamma. But the CO group, it has methyl group. So this is having alpha carbon. Similarly, in diphenyl ketone, both of them are benzene ring and it cannot have alpha beta carbon as their positions are identical to each other. So to identify specifically, you can make that functional group with a box. So to which it is present alpha carbon, and here it is no alpha beta gamma because of benzene ring, and here it is the functional group having alpha beta gamma, and in this case this is ketone having 2 alpha group, and in this case the ketone having ethyl and methyl, and here the ketone have methyl and phenyl, and this is the functional group having 2 phenyl groups. IUPAC nomenclature of aldehydes and ketones. So in IUPAC nomenclature the suffix is AL because aldehyde they have the first 2 letter AL that makes suffix of aldehyde, and in ketone KETONE here this one that makes suffix of ketone. So aldehyde AL that makes the suffix of aldehyde the functional group, and in ketone the ONE that makes the suffix of functional group, and both aldehyde as well as one, that AL and one should always come to the suffix, but when the ketone as well as aldehyde present together in a compound, organic compound having both ketone as well as aldehyde in its structure, there one of the functional group becomes the substituent, other functional group becomes the part of the chain. The ketone is taken as the prefix of the compound like oxo. Why it is called oxo? Because I have the structure of ketone is CO. The ring, the carbon that makes part of the chain. To the part of the chain the oxygen is present. That's why the oxygen is taken as oxo as a substituent. And the position of oxo should also be identified in their compound. Why? Ketone goes the suffix, that means ketone goes the part of the chain and aldehyde goes the functional group. This is because the aldehyde that is more prior than ketone. So as per the priority rule, aldehyde that makes the part of the chain as well as its functional group, and the ketone becomes the substituent of the chain. Let us discuss about some of the compound having the different number of carbon atom. Here the first member of aldehyde is formaldehyde because it has only one carbon. Its corresponding acid we discussed about formic acid, and hence the name of the compound is formaldehyde. It is its common name. But as it has only one carbon atom, its root word is meth and has no double or triple bond, so primary suffix ane, and the functional group is aldehyde, so the secondary suffix is al. That's why name of the compound is methanol. See, you have to make the sound difference. Methanol, that is OL, methanol, that is AL. So all for alcohol, al for aldehyde. So the sound that makes what kind of functional group is present in the compound. Similarly, you can go with this 2 carbon having aldehyde. It is acetaldehyde and it has 2 carbon atoms. So its root word is eth and no double bond. So the primary suffix ane and the secondary suffix is al. So the name of the compound is ethanol. Ethanol. And the 3 carbon, it is propanaldehyde as it is common name, and its IUPAC name will be having 3 carbon atom, prop, no double bond, so ane, and the secondary suffix is aldehyde. So the name of the compound is propanol. And here we have the compound where methyl group is present at the second position. So the name will be part of the chain 1, 2, 3. Second position has methyl and the chain has 3 carbon. So its root word prop, and it has the second position of methyl. So it has the prefix 2-methyl propanol. So the name of the compound 2-methyl propanol. It is its IUPAC name. What about its common name? It is isobutyl structure, 4 carbon with the iso structure. So its common name will be isobutyraldehyde. The next compound, it has a double bond structure as well as a ketone and one more substituent also present. So to name the compound, let us assign the numbering 1, 2, 3, 4, 5. So fourth position it has methyl group, and third position it has a double bond, and the second position it has a ketone. So the functional group of the compound is ketone. Along with that it has two more substituent also. So we may find its common name is actually mesithyl oxide. And its IUPAC name, the straight chain, it has 5 carbon atoms, a root word pent. And its prefix, fourth position methyl is there, so 4-methyl pent. And it has a double bond at the third position, so 4-methyl pent 3-ene-one. So the name of the compound 4-methyl pent 3-ene. So in this the position of the one is second one, so you have to take it as 3-ene-2-one. So why do we give here the position of CO group? Because the CO group that can change their position with respect to all the 5 carbon atom, and double bond can also be changed their position. So if there is a possibility of changing the position of CO group in a compound, where we have to give the position of the ketonic group itself. Here I have a closed structure, the ring. It has 6 carbon atom. So for this the closed prefix is cyclo. And how many carbon I have? 6 carbon, hex. It has no double bond. So the primary suffix is ane. So I got cyclohexane over. So this hexane that makes the number of carbon atom present in the ring. But in addition to the 6 carbon, I have one 7th carbon of aldehyde. How to name this one? See, in such cases, the aldehyde is termed as carbaldehyde. Carbaldehyde that includes the carbon C. So total number of carbon in this is 7. So 6 plus 1, 7, that satisfies number of carbon in the given structure. So in the closed structure or more than one CuHO groups are present, there we have to make use of carbaldehyde. So it has only one CHO. If I write one more CHO to the same cyclohexane, what I will do? It is cyclohexane, but the first and the second position of the ring, it has 2 carbaldehydic group. So the name it goes cyclohexane 1,2 dicarbaldehyde. Such a way we have to name. So for this one I can write the name is cyclohexane carbaldehyde. And the other, where I make 2 CHO to the adjacent position of cyclohexane, there it is cyclohexane 1,2 dicarbaldehyde. You know well, where the consonant comes, we have to retain the letter E. Where vowel comes, where we have to remove the letter E. And one more thing we can find, see, you may have the aldehydic at 3 positions of the chain. First carbon, second carbon, third carbon. All these 3 carbon, they have 3 CHO group. So when you have only one CHO, that can make a part of the chain and you can have the suffix of Al. But as it has more than one aldehydic group, then these aldehydes to be termed as carbaldehyde. Where and all present? 1, 2, 3 position. So chain, how many carbon I have? Only 3 carbon, and it has no prefix at all. So the name is propane, because a straight chain 1, 2, 3 tricarbaldehyde. So the name of the compound is propane, and in this case I have aldehydic group as well as the ketone. So 2 functional groups are present. As per the priority rule, aldehyde makes the functional group and the ketone goes the substituent of the chain. So you have to identify their position 1, 2, 3, 4. Third position ketone is present and the third carbon becomes the part of the chain and oxygen alone makes substituent. So you have to write it is 3-oxo. How many carbon? 4 carbon. So 3-oxo-butane-al and aldehyde is at the terminal position. So the name of the compound is 3-oxo-butane and its suffix is al. So butanal. So such a way IUPAC names are given for aldehydes and ketones. Here I have taken only the samples of the compound only to introduce the concept, and you may practice with more number of compound whatever given in reader, or you may find it in some other sources also. Nomenclature of aromatic compounds, let us see some examples. So here we have the aldehyde as well as substituted aldehyde, and in this case we may have that aldehyde is present directly to the carbon, that is the benzene ring, and in such cases actually the name is given for this is benzaldehyde. This benzaldehyde that could be taken as common name as well as its IUPAC name. Actual IUPAC name is phenyl methane al. But benzaldehyde itself taken as common name as well as IUPAC name. Likewise, this is also acetophenone and the next one benzophenone, that's also make its common name as well as IUPAC name the same. But in substituted one, you have to identify the priority of the compound. So aldehyde that makes that more prior than OH. So OH that goes the part of the substituent. So it is called 2-hydroxybenzaldehyde. And in this case, I have one CH3 group and one CHO group. Actually, it is called toluoldehyde. Actual name is 1,2, so it is 2-methyl benzaldehyde. In this case, it is a cyclohexane, but it has a doubly bonded O, and the carbon that goes part of the ring itself, no more number of carbon increases. So it is called cyclohexane as it has 6 carbon, but with the functional group of doubly bonded O, it ends with one. So the name of the compound is cyclohexanone. That's all the nomenclature of aldehydes and ketones. Structure of carbonyl group. Carbonyl C double bond O. So in this carbonyl group, the carbon atom is sp2 hybridized because it has 3 sigma bond 1, 2, 3. So you can find the sp2 carbon out of its valency 4. So you may find 3 of the electron in sp2 orbital and one more electron is at its p orbital. So this 3 sp2 hybrid orbital, one of the sp2 gets overlapped with one of the p orbital of oxygen atom, so that it develops a sigma bond between carbon and oxygen. And this carbon, it has 2 more sp2 hybrid orbital that may overlap with either 1s1 orbital of hydrogen atom or sp3 hybrid orbital of an alkyl group. So in case of aldehyde, you are getting such overlapping. But in ketone, the other 2 sp2 hybrid orbital of the carbonyl carbon overlaps with sp3 hybridized orbitals of both alkyl group. And in this case, upon overlapping, it can able to develop 3 sigma bond in its structure. But both of carbon and oxygen, they have one more odd electron in their p orbital. Besides sp2 hybrid orbital, carbon has one p orbital electron and oxygen one of the p orbital, particularly pz orbital that makes sigma bond with carbon. So oxygen, it has one electron in its py orbital. Similarly, carbon would also have one electron in its py orbital. So these 2 py orbitals of carbon and oxygen, just they are perpendicular to the plane of the structure. sp2 hybridized carbon, so the geometry of the molecule will be trigonal planar. So to the trigonal planar, these two filled p orbital of carbon and oxygen undergoes sideway overlapping or lateral overlapping that makes the formation of pi bond. So in a carbonyl group, the carbon oxygen is made up of one sigma bond and one pi bond. And carbon, it has the two more sigma bond with its substituent. And here, being the sp2 hybridization, carbon, it has bond angle of 120 degree. So about carbon alkyl hydrogen or carbon alkyl alkyl, carbon oxygen, everything it has the 120 degree. So the geometry of the molecule is trigonal planar. Okay, due to the presence of pi bond, that bond that can be delocalized, and delocalization takes place between carbon and oxygen because oxygen is more electronegative than carbon. So oxygen, as it withdraws the pi electron, that develops a negative charge over the oxygen and positive charge over the carbon. So that can be represented by two structures. Those are called resonance hybrid of carbonyl group. And in this case, the dipole moment of carbonyl is much greater than that of ethers. Therefore, the polarity of carbonyl group is also much higher than ethers. So, as a result of the delocalization of pi electron, you may find the oxygen develops a negative charge and carbon that makes a positive charge. So, due to the presence of both positive and negative charges, it has the nucleophilic center as well as electrophilic center. The nucleophilic center is referred as the electron rich and hence that has Lewis base structure. And in this electrophilic center, it is electron deficient. That's why that makes the Lewis acid of carbonyl group. So, as it has both the positive and negative terminal of the carbonyl group, you know this will undergo nucleophilic addition reaction. So, nucleophilic addition reaction carried out only between the carbonyl group of carbon and oxygen. Moreover, the oxygen is much electron rich because its 2 of the p orbital electron is found to be in a sigma bond as well as in its pi bond. Besides this, it has 2 more lone pairs of electron that always present about the oxygen atom. So, you may find after the delocalization, oxygen will get 3 pairs of electron. Before delocalization, oxygen has 2 lone pairs of electron because these are referred as non-bonding electron pair. So, this also makes that oxygen atom is more electron rich and hence it is a Lewis base. So, this is what the structure of carbonyl group, and we have discussed about the polarity of carbonyl group also, and the polarity of carbonyl compound is much higher and hence they may undergo nucleophilic addition reactions. Preparation of aldehydes and ketones. These methods already we have discussed in our alcohol chapter as well as in alkenes and alkynes of hydrocarbon chapter. So, once again let us have a glance. Alcohol, we know the primary alcohol and oxidation by mild oxidizing agent like chromic oxide that is oxidized to aldehyde. Or if I have a secondary alcohol that gets oxidized to ketone. So, why do we take mild oxidizing agent? Because we need to have only the carbonyl compound. In place of mild, if you have strong, it will go to carboxylic acid. So, for the oxidation of alcohol to have aldehydes and ketone, we should take mild oxidizing agents like chromic oxide. And we have one more oxidizing agent, that is PCC, called pyridinium chlorochromate. This pyridinium chlorochromate is a selective oxidizing agent because it does not alter the position of double bond. It can oxidize only the primary alcoholic group. So, let us have that example also. Just I refer over here. in which when an unsaturated alcohol, see that 1, 2, 3, 4. So second position it has a double bond. The name is but2-in-1-al. So when it is oxidized by pyridinium chlorochromate, here that oxidizes only the primary alcoholic group to aldehyde. Suppose if you have chromic oxide over here, see this double bond will also get oxidized. So to prevent the oxidation of double bond, we have to take the selective oxidizing agents for such cases. So after the oxidation of alcohol, we can prepare both aldehydes and ketones from ozonolysis of alkene. So in which the ozone is that makes ozonide structure with the doubly bonded carbon followed by its hydrolysis with the metal and water. We are getting the carbonyl compound. The nature of carbonyl compound will be based on the nature of the alkene. If you have a symmetric alkene, you will get two identical carbonyl compound. If the alkene is unsymmetrical, you will get two different carbonyl, both the aldehyde or both ketone or the aldehyde ketone you can get. Suppose if I have an unsaturated alkene of propene structure. So the ozonide that can make only between carbon-carbon double bond and all other groups will be the substituent of doubly bonded carbon. So I have this ozonide structure. In this one of the carbon has CH3H, the other carbon it has two hydrogen atom. So how the bond will break? See that and all we discussed in hydrocarbon chapter itself. Once again just I will give it to you. So because of the breaking of CO and OO bond, you are getting a pair of electron. That pairs of electron makes one more bond between the CO group. So in this I have, this is the breaking of the bond. So I have CH3 C double bond OH. This side CH2 double bond O. This is nothing but formaldehyde HCHO. So when an unsymmetric alkene is taken, I will get two different aldehyde. That may also be two different ketones. But symmetric will give identical. And one more thing we have informed that the terminal position of double bond should always give a formaldehyde as one of the products. So in this the double bond is at its terminal. So you are getting formaldehyde as one of the product. The next one from alkynes. Alkynes also we studied. During the hydration of alkyne, they form enol and from which a carbonyl compound is formed. So here the C triple bond C, this is also depends on its symmetric or unsymmetric, you will get different product. Only the ethine can give acetaldehyde and all other alkynes will form only the ketones. They do not give aldehydes. So when the C triple bond C is added with the molecule of water, you may find one of them that goes like this. So we can have COH with the CH structure, and here the hydrogen atom of OH group that moves towards the doubly bonded carbon. So we are getting the structure like that. So the position I have altered, but that doesn't make any difference because it is symmetric only. So in this case also you can have this goes with carbon and the other one will go with OH group. So I am getting this enol. From this the hydrogen atom of OH migrates towards the CH2 group. So we are getting CH3 C double bond OH. This is symmetric, and in this case I have taken propyne. The previous one is ethine, this is propyne. In unsymmetric, we have to follow the Markovnikov rule. So the OH should go to the secondary, that is the CH3 carbon with more alkyl, and the CH carbon will take the hydrogen. So we are getting the unstable structure of enol, and from which the hydrogen atom migrates towards the CH2 group. We are getting acetone as the product. This is ethanol and there it is acetone. Preparation of aldehydes. First reaction, let us see Rosenmund reduction. It is the name reaction. In Rosenmund reduction, the acid halides are converted into aldehydes. So we have to take either aliphatic compound or even aromatic compound, we will get the corresponding aldehyde of the reaction. So if I have the benzoyl chloride, it undergoes reduction where the COCl is converted into CHO. So here the acid chloride undergoes reduction with the hydrogen in presence of palladium coated with barium sulfate. There it forms aldehyde and HCl. Similarly, the acetyl chloride, it is acetyl chloride or it is also ethanoyl chloride. This is benzoyl chloride. This also can be reduced by palladium coated with barium sulfate to form aldehyde. So, acetyl chloride that gives acetaldehyde as the product. Okay. Why we are taking barium sulfate over palladium? See, palladium is a catalytic reducing agent, and this catalyst, it can absorb a large volume of hydrogen. So when it acquires large volume of hydrogen, we do not get aldehyde. Instead, the reaction will stop up to the formation of alcohol, because acid halide gives alcohol the product. But we need to stop the reaction up to the formation of carbonyl. So here the barium sulfate that occupies the surfaces of palladium largely, and it provides very less area for hydrogen. So accumulation of hydrogen is reduced, and hence the reaction is stopped up to the formation of aldehydes. So barium sulfate behaves as catalytic poison to the catalyst palladium. Catalytic poison means to reduce the catalytic activity of the catalyst, we will add suitable material. Those are said to be catalytic poison. Stephan reaction. In Stephan reaction, nitriles are converted into aldehydes. Nitriles are nothing but cyanides. The common name is cyanide and IUPAC name is nitrile. Nitrile is a C triple bond N structure. And this nitrile, actually it forms aldehyde through the formation of imine. This is said to be imine. A CH double bond NH structure is called imine structure. So this Stephan reaction, it proceeds in presence of stannous chloride and HCl. Stannous chloride actually tin 2 chloride. When it reacts with the HCl, that is converted into stannic chloride and hydrogen. This liberated hydrogen is used for the reduction of nitriles. So this hydrogen, it shares between the C triple bond N, and hence we are getting CHNH. As 1 mole of the hydrogen added between carbon nitrogen, triple bond is reduced to double bond. It forms imine. This imine followed by hydrolysis, we are getting aldehyde and ammonia. So this NH group that can add with the 2 hydrogen atom of water with RCHO, we are getting aldehyde. So this Rosenmund and Stephan reactions are the most important reactions of the name reactions. From nitriles, before we have seen about Stephan reaction. In Stephan reaction, nitriles are converted into aldehydes, but the reducing agents we have selected stannous chloride and hydrochloric acid. But the same nitriles that can be reduced to aldehydes, but in presence of dibal-hydride. What is called dibal-hydride? It is diisobutyl aluminium hydride, and it is a selective reducing agent, just like PCC. PCC is selective oxidizing agent. Here dibal-hydride is a selective reducing agent. So it can reduce only the C triple bond N. It can reduce only the nitrile, and all other parts of the compound will not be disturbed. Not only nitrile, this dibal-hydride may also reduce the esters. So let us take the example. The structure of aluminium hydride, diisobutyl. So isobutyl 2 times present, CH3, CH, CH3, CH2, CH3, CH. CH2, CH, CH3. So 2 times of butyl group, isobutyl group is present along with the hydrogen because the valency of aluminium 3. So that can be condensed to CH3, CH, CH3, CH2 twice aluminium hydride. So how the name? Di-isobutyl aluminium hydride. That's why it is shortly known as dibal-hydride. So the RC triple bond N nitrile, upon the reduction of nitrile, it gives imine. Just like Stephen reaction, here the intermediate is the formation of imine only. Only the difference of Stephen and this reaction is the reducing agent. So imine followed by acid hydrolysis, it is converted into RCHO and NH3. Or you can take an unsaturated nitrile. What about its name? 1, 2, 3, 4, 5. So 5 carbon, it is pentane, and the third position has a double bond. So the name is pent3ene nitrile. So this is on reduction with the dibal-hydride. You may find only the cyanide group is converted into imine, CH double bond NH. Followed by the hydrolysis, we are getting aldehyde and ammonia, and the reduction may also take place in doubly bonded carbon that can also be converted to CH2, CH2. But the reducing agent is the selective one that can affect only the cyanide, not about the position of double bond. And esters can also be reduced to aldehydes. So here I have taken, it is methyl propanovate. When methyl propanovate is reduced by dibal aluminium hydride, the cleavage of bond takes place between acyl part and alkoxy part. So here I can add a hydrogen, here I can add a hydrogen. So we are getting propanol as well as methanol. So this is reduction of nitriles either by Stephen reaction using stannous chloride and HCl, or by using dibal-hydride. We can reduce nitriles to aldehyde through the formation of intermediate imines. Preparation of aromatic aldehyde, say benzaldehyde. So the first method of preparation of aromatic benzaldehyde is from etard reaction. In etard reaction, we are going to take toluene. So when toluene is treated with the chromyl chloride in presence of carbon disulfide, this chromyl chloride is actually an oxidizing agent. So this oxidizes that methyl part into the chromium complex of toluene derivative. Followed by hydrolysis, we are getting benzaldehyde. See, in this toluene, the 2 of the hydrogen simply adds to 1 of the oxygen atom like OH. So 2 times the chromyl chloride is taken because of the 2 hydrogen atom involved in the reaction. We are getting OCrOH, twice. When it is hydrolyzed, it undergoes acid hydrolysis, that complex and CH bond breaks. So we are getting over here oxygen, benzaldehyde is formed. This reaction is known as etard reaction. Same toluene that can be oxidized by chromic oxide, but in presence of acetic anhydride. At 273 to 283 Kelvin, it forms a benzalidine diacetate. Once again, the 2 acetate group that gets added with the CH3, 2 hydrogen atom of CH3, you are taking CHOCOCH3 twice. So 2 of the hydrogen is replaced as water molecule, that is oxidized to water. We are getting benzalidine diacetate. Followed by hydrolysis, here the bond it breaks between, so we are getting benzaldehyde. So when toluene is oxidized by chromic oxide in presence of acetic anhydride, that forms benzaldehyde. Similarly, when toluene undergoes substitution reaction in the methyl group by halogen, we will get gem dihalide. When it is hydrolyzed by alkali, the 2 of the chlorine atom can be removed as NaCl and we are having gem diol. This gem diol highly unstable, so a molecule of water is removed, we are getting benzaldehyde. And last method of preparation of benzaldehyde is Gattermann-Koch reaction. In this, benzene is converted into benzaldehyde when it is treated with a mixture of carbon monoxide and hydrogen chloride in presence of anhydrous aluminium chloride and copper 1 chloride that forms C6H5CHO. So these are the different methods of preparation of benzaldehyde, out of which Etard reaction and Gattermann-Koch reactions are name reaction. In all these cases, you may find that toluene is taken for the preparation of benzaldehyde except Gattermann-Koch reaction. Preparation of ketones. Ketones can be prepared from acyl halide or from Grignard reagent or by Friedel-Crafts method. Acyl halide, first of all, acyl halide has to be treated with dialkyl cadmium. This dialkyl cadmium is actually prepared from Grignard reagent and cadmium chloride. This is dialkyl cadmium. So when Grignard reagent is treated with the cadmium chloride, this MgCl2 will be removed. So we have to take 2 times of Grignard reagent. So I am getting R2CD. MgCl2 is being removed. This dialkyl cadmium, when it reacts with the acid halide, twice the time of acid halide is taken. So we may get this cadmium chloride will be removed off CdCl2. We have RCOR plus RCOR. So we will get 2 times of ketone. So this is the preparation of ketone from acyl halide, in which we have to take dialkyl cadmium. Then from Grignard reagent. In Grignard reagent, actually nitriles are converted into ketones. So any nitriles we can take when this nitrile is treated with the Grignard reagent. We know the one of the pi bond that attacks the MgBr and the CH3 group attacks the carbon. We are getting CH3, CCH3, triple bond into double bond NMgBr. Followed by hydrolysis, the bond breaks like that. So here oxygen, here the 3 hydrogen, here the OH. So we have to take 2 times of water molecule, getting ketone, ammonia and the magnesium derivative. The last method, Friedel-Crafts acylation and benzylation, in which we can prepare either substituted ketones or even ketones itself. When benzene is treated with acetyl chloride in presence of anhydrous aluminium chloride, one of the hydrogen atom of benzene ring is substituted by the CH3CO group. So we are getting acetophenone and HCl. Or in presence of benzyl chloride C6H5COCl, once again the HCl is removed and the place of hydrogen substituted by benzoyl group. So we are getting benzophenone. So by Friedel-Crafts method we can prepare both benzophenone as well as acetophenone upon acylation and benzylation. That's all the preparation of ketones. The last method of preparation of aldehydes and ketones from calcium salts of fatty acids. Fatty acids, the alkyl group should be the long chain. So when this carboxylic acid treated with the base, acid base, it forms salt and water. We are getting calcium salts. This calcium salts depends on the size of R group. You can get formaldehyde, the simplest aldehyde, acetaldehyde or ketone. But the R group only decides what kind of aldehydes or ketones you are going to prepare. So let us take first of all, what are the formulas for calcium formate and calcium acetate? Suppose if the R is only hydrogen, that will be formic acid, so you are getting calcium formate. Or if R is a CH3 group, then you will get calcium acetate. Let us take these 2 salts to prepare the aldehydes and ketones. Let us prepare first of all acetaldehyde. Acetaldehyde, it requires both calcium formate and calcium acetate. When both of the salts are distilled at high temperature, two molecules of calcium carbonate is eliminated and you may find this CH3CHO plus CH3CHO. So when calcium acetate and formate, the two different calcium salts heated, we are getting acetaldehyde and calcium carbonate. So to have the aldehydic group, you have to take calcium formate as one of the fatty salt. And if you have only calcium acetate, then there is a loss of calcium carbonate from the same salt itself, and we can have CH3COCH3, acetone and calcium carbonate is formed. Or if you have calcium formate alone, once again upon distillation calcium carbonate is removed, we can have HCHO, formaldehyde is formed. So to form other than formaldehyde, if you want any other aldehyde, you have to take the respective salt of calcium along with calcium formate. But all other calcium salts upon heating on its own, they can give the symmetric ketones like this. Okay students, let us close our today's session. Today we have discussed about the introduction part of aldehydes, ketones and carboxylic acids, the nomenclature of aldehydes and ketones, and the preparation structure of aldehydes and ketones. So we will see the next session with the properties of aldehydes and ketones. Until then, bye bye.